So I'm going to plug in a 1, but I want it to take 1 over and square that number, right? So I'm going to go over to L2, and watch me carefully. I'm going to up arrow here, and highlight L2, and I'm going to type 1 division L1 squared. Okay? That's what I'm going to type. 1 division bar. Where is L1 on the screen? You got to hit second 1. Does everyone see that? But I want to raise it to what power? Raise it to the second. And what will it do when I hit enter? It's magic. Ooh, thank you. Isn't that cool? So I just wanted to do that for me. So if you like doing this, now some people go, well, forget this, I'll just put it on a blank screen. But I just want to now get all this added up. So I'm going to hit second mode. Was everyone okay with that? Kind of network, all right?
No, it's giving me an error message. It's fine.
Oh, okay. I can show you later.
Okay.
Hey, so I'm just going to blank out of here, Connor and everyone. I'll just, how do you get out of the screen? Just second mode, right? With. And I am going to go to a menu called list. It's second stat. Second stat. And there's an operation, see that names op to math? I'm going to arrow over to math. And look what number 5 says. Number 5 says what? It says sum. All right, I want to sum something. What do I want to sum? Which list? So I'm going to put in an L2. So to do L2, I got to hit second. Now, if this you found annoying, you could just add these up on a blank screen. Or you might prefer Microsoft Excel, but since we had to add up all these terms, what do we get? 1 point, I better write this down. 1.5497. (677) Cool. Love it.
You just do math zero. Yeah, that's what I was gonna say.
Math 0, you can do that. Yep, absolutely. That's totally fine. Hey, is everyone okay with that? Nice. Hey, so now, I want to talk about that math 0. I just want to up arrow here. It's a summation button. Everyone see that? If you have it. Now, not everyone has a what? Math 0. This is an upgraded calculator, so that's why I wanted to show that. Like, raise a hand. Who's got a TI-83? Yeah, they don't have that, you know, in terms of that summation thing. So they got to go through this method. But Math 0 has a what? A summation button. It was Math 0. And you go, oh, my calculator has that. I want to hit it, and look what it shows. You hit enter. And it's got everything, and I just type everything in, right? I can use X here, true? X, I can put a 1. How far did I go up to? Oh, up here, up arrow there. I'm going to put a 10. And let me right arrow. What was in this expression? 1 divided by X caret 2. I'll just tip what? Cool. Who's got the newer models? You might find that a lot easier. You don't have to go into L1. Absolutely do that. Awesome. Now, what's this remainder theorem say? If we use 10 terms, then the 10th remainder must be less than the, if we use 10 terms, must be less than or equal to this. So I'm going to hit the lights, and I'll come back to the screen. I just want to get the lights up here. This remainder theorem is very simple. Very simple to understand. It's saying if I use 10 terms, then the remainder, the error in this problem, has to be less than or equal to this. And I'm using 1 over x squared because that's like that p series. The only thing is, what was this antiderivative? Can you help me evaluate this? It's an improper integral. What we're saying is the remainder, the error for what we just found out, how close is this to the actual sum? We can estimate it. It's got to be less than or equal to this. What is that integral? So that's going to be a negative 1 over x, the antiderivative, okay? And I got to go from t to a what? A 10, I'll send my limit towards infinity, and you get what? You get a 0, subtraction of 1 over 10, which becomes a what? 1/10. So, what is that? You might want to look at this as a decimal. What's that as a decimal? 0.1. This is what we're saying. This was pretty close to the actual sum. The error We're like within 0.1. We know the error is within 0.1. Pretty cool, huh? That's 1 decimal place. We only did how many terms? 10 terms, right? So I just want to point out, we're within this what? 0.1 here. So, what I could do is I'm going to leave this up here. We know it's got to be within what? 0.1 or 1/10 of the actual sum. But this is like an upper bound. So there's the upper bound. Can you go over here? Can everyone read what it says right there? Same thing, but it says integral starts at, ABC it says n plus 1. So if I used n equal to 10 here, n equal to 10 here, right now I'm saying, okay, this is really close to the actual sum, which we don't know, but it's within 0.1 of the actual answer. What would be a lower bound? I'm like, well, let's go in. I'm going to make this 11, okay? So I'll do that. Now if you got the TI-83, you know what to do. You're going to have to go on the list and do that. And I'll hit the light. So I want to do this in case I got my TI-83 people here, but some of you might just do what? 1 to 11. Does anybody know how to make that re-emerge on a screen and you can just change it? Upper. Second enter. So if you want to, you could hit second enter. I'll hit the second enter. Can re-emerge what you just had. It allows you to edit it. So I'm going to do that. But if you got the TI-83, you're going to have to go back to the list and add an 11 in there. And do this. Now, which number do I want to change? I want to change to what? Change this to a 11, right? Hit enter. Okay, now I got a 1 point what? 558. All right. So 11 terms, it'd be what? 1.558. Is that okay with that? 1.558, what was the other number? The 1.449, true? I want to make sure I got the same number there. That's cool. But what we're doing is, I'm going to write this another way. I'll hit this light here. I'll turn this off. This is the last thing before we do this. This was 0.1, right? What would R11 be? We get this equal to what? Integral from 11 to infinity? Can you help me do that? What would you get for that error? 1 over 11. By seeing this, we know we're going to just get what? 1 over 11. So this is what we're saying. I'm saying that this sum right here is going to be between, right? I know it's less than 1.45497677731 plus, what was that upper bound? It was what, 0.1? I'll write it 1 time. And the lower bound is, I'm going to use the same number, 1.549767731 plus 1 over 11. This is what I know. Just by looking at 10 terms. I know that has to be in between these. And I only did 10 terms. No, because we're just looking at like what the error would be in between these. You'll notice, because this number, this is interesting. This is actually lower than it, isn't it? 1 over 11 is smaller than 1 over 10. But you'll notice it gives you a really good range of where that sum would be. We know that that answer right there, I'll put this again, has to be between, hey, can someone do this for me on a calculator? What is that number right there? What's 1.549767731 plus 1 over 11? You know it's got to be somewhere in here. And thanks for being paid. This is kind of fun to do. We're trying to emphasize that when these sums we're dealing with in this whole chapter 11, a lot of them we don't know the answer to unless it's a geometric series.
1.64067.
And that's this one?
Yeah.
1.64067, that's far enough. How about over here? What's this? Oh, I just got to have a 0.1 where? Don't I go with it? And when I know the sum is somewhere in here. And I already looked at how many terms. So I want to label things. What was this? This was the summation to how many terms?
11.
Plus, that was summation of 10 terms, but I looked at that remainder concept, right? So I thought of that plus R11, and over here I did the summation of 10 terms, but I used the end. Does that make sense? See how this number was from 10 to infinity. This was from 11 to infinity. Remember how we got those two answers?
What do you have two comparison operators? 1.6406 is greater than, less than, equal to?
This means less than or equal to.
Oh.
We're saying that this is the actual sum, and it means it's got to be between. So how about that, between? It's got to be between.
Oh, okay, so your 7 kind of look like a comparison, I'm sorry.
Yeah, it's okay. Is everyone okay with that? Cool. Now, there is a mathematician who figured out this sum exactly. His name's Euler. You know what he got it to be? He figured it out as this. Thank you, Euler. He figured this out. He figured out that this summation. It's a p-series, right? He figured out that p squared. He proved it. But now we're talking about Euler, one of the greatest mathematicians ever. And he figured out this came out to be exactly pi squared over 6. Now we hit that on the calculator. What's 3.141592665 squared over 6? What do you get? 1.6449 inside there. But do you see the idea? Now you might think, oh, so did Euler figure out 1 over n cubed? No. Has anybody figured this out? Exactly. We go to that p-series. Has anybody figured out that p-series exactly? The answer is no. You know? So it's really interesting how it's like a lot of times we're just left what? Estimating. And we can use technology now to estimate this stuff. Be accurate to 8 decimal places. Store it into calculators. Store it into computers.
Is that the same guy that gave us the E constant?
Yeah, he's the one who said, let's call that E for the natural base. We're going to call that E. And he did a bunch of other things. Oh, yeah. He's brilliant. What's your book again, Chris? What's that cool book you have for calculus?
Oh yeah, the foundations of differential calculus.
For
Euler.
Euler, yeah. Very cool.
Yeah, shoot.
All right, I want to do the comparison test. And I'm going to start with this one.
Those things pronounced Euler. I guess they're screwed up.
Hey, everyone, 11.4? Let's check out this problem. I'm hoping you love this. I'm hoping you like this. We're now talking about a new test, the comparison test. Didn't we already do this problem? Yeah, but you might find an easier way to look at this problem. Like, hey, you might remember that integral? It was an arctan, it was kind of messy. Maybe I wasn't sure about its limit and stuff. Well, with this problem, what we're saying is, boy, what if we can compare it to something easier? What I mean is, what if I can just get that stupid 9 off there? And I can compare this to 1 over n squared. Isn't that a p-series? And we already know about p-series. Let me hide that. If I hide that right there, and when that p-series, is that convergent or divergent? Convergent, right? P-value is greater than 1, and p-series is greater than or equal to 1. So rather than going through that entire integral test, which was great, and it was nice, what's cool about the comparison test, it can just save me a lot of time in writing. As long as, now this is what has to happen. A sub n, that means this guy, I'm going to call this A sub n. Hey, you're A sub n. And I'm going to compare it to something easier. This guy. So this is who I'm going to compare it to. So, by that, I'm going to call this B sub n. I'm going to call you B sub n. All right. So let's compare it to this. And if this series converges, and A sub n is greater than or equal to B sub n, that will be for divergent. But I want us to focus on, I'm going to put a big dot here. if A sub n is less than or equal to B sub n, and if this series converges, then this one will also converge as well, okay?
So do we just get P choose what P sub n is?
That's right, you get to choose this.
Okay.
You choose something simple, something that's really easy.
Do we usually try and make that one based off another rule, so it's...
Yeah, something that you can compare to it. So what do you know about 1 over n squared plus 9? And 1 over n squared? Which one's smaller? Sometimes it's hard to tell.
1 over n squared plus 9.
Let's plug in a number. Yeah, a lot of you know. Let's plug in a number. If I plug in a 1, what's that?
1.
1. If I plug in a 1 over here, what do you get?
1/10.
Which one's smaller? Ah, so this one is going to always be less than or equal to this for n equal to 1 and higher, right? That's true. All right, so you're less than this. This is less than this. Well, as long as this guy converges, then this one has to converge. This will converge as long as this converges. Okay? Does this converge?
Yes.
This converges. And so going off what we just said, we chose something easy that was very similar to this. And because A sub n is less than or equal to B sub n, the series A sub n converges. Remember, I'm just going to justify this, but I don't have to write as much as I did with that integral test. This series converges by the comparison test. I'm okay if I write CT. And let me just write one more thing. I do have to point out why this converged. Why did this converge? This converges by the comparison test because this series right here, you remember what I called that? B sub n? B sub n converges by what method?
P series.
And I'll put that. P series, P is greater than or equal to a what? 1. Or actually, I'm sorry, P is greater than 1. You were talking about that earlier. I gotta make sure I get that right symbol right there. P series, P just has to be greater than 1. If P equals 1, it diverges, doesn't it? So this acts, but everyone check out the writing here. This converges by the comparison test because the series B sub n right here converges. It's a P series with P greater than 1, or P equal to 2. Cool. So I definitely chose something like that.
Would you expect that writing on the test, like that exact wording?
Exactly. That's what's expected because when I write the directions on a test, I want to point out what I write. I write something like, hey, be clear in your justification. So I say, number 1, I'll write this. I'll say, make sure you name the test. You want to name the test you're using. So in this case, I was using the what? The comparison test. But you can abbreviate it. And then I explain what went on with the comparison test. I said, hey, this converged because by the comparison test, this series I was comparing it to, when we wrote it down, there's B sub n, converged as a P series with P greater than 1. So excellent. Do you notice though with the integral test, it took a little bit more writing, didn't it? I don't know, you might think it's just as easy. I shouldn't say one's easier than the other. But it gives you another option, doesn't it? It gives you another option. Cool. My only worry about comparison tests is when someone uses it and they got this backwards. See, if that's backwards, then I can't use it. Can I give you an example? I want to give you an example that we go, oh, I thought I could do this. So, what was the one I did close to this? When I did it 15 minutes ago, I had like an n over n squared plus 2. Remember that? Can you try that? So here's, I'm not like this, like warning, be careful. You can tell me times I've seen something like this on a test. You're like, oh, this student had it, but they just was missing one thing on it. I'm like, professor, I knew it diverged. I go, yeah, but you used the wrong test. They go, I can't use this test? And I'm like, no, because this wasn't true. Or this wasn't true. So I want to just look at something like this. Didn't we do one like this before? Well, obviously, who would you want to compare this to? Remember, Connor, I'm trying to look for something that's similar to this, so I'll hide that plus 2. who could we maybe compare it to? Yeah, he goes, maybe we could compare it to n over s. That way we can see who's less than the other, right? Well, what is this simplified? By the way, do you recall this did diverge by integral test? Does everyone remember? Okay, so we're like, oh, okay, this is 1 over n. And this diverges, doesn't it? This diverges. By what? It's a harmonic series. It's a p series with p equal to what? 1. Here's the trouble though. What does this say right here? I can use the comparison test. If the series I'm comparing it to diverges, but what has to hold true? A sub n's got to be greater than or equal to b sub n. You follow me? And look carefully. Is a sub n greater than or equal to b sub n? That's the trouble. So what I'm saying is I'm not going to use the comparison test on this problem. Connor, do you follow that?
Yeah.
I just want to make sure. So that's the danger. Where you go, but I know. Remember this diverged? So someone's saying this diverges by comparison test, and then they justify it this way, and they're like, "Man, I lost all these points." It's because they're using the wrong test. And it was all because it came to that little one. That wasn't holding true, right? Is a sub n greater than this? We're like, no. This is what? This is lower than that. So what I'm saying is, I can't use the comparison test on this problem. I would use the comparison test. What would I use? Use the integral test. The integral test is easy. Great. Hey, great job with that.